Hi, hello. Welcome to section number 2. Which, again, I am so excited for. I can't tell you, and honestly, I shouldn't tell you because it makes me seem lamer. How much I look forward to this each week. How much on Friday I was like, ooh, I get to make a rough draft of this lesson. Ooh. How I went to bed last night. Don't do this. Do as I say and not as I do. I went to bed at like 4 a.m. because I was like writing it out all nice and trying to make my reaction coordinates look like not crappy. So I'm really glad to be here. Um, and I'm excited to chat about this with you, which again, I've lost all street cred. I lost it immediately when I said aspartic acid. So here we are. But game plan for today, we're going to start off with a foundations and review section specifically to help support us for mechanism, because largely that will be the bulk of the course going forward. We're going to have one more topic that's a little bit more kinetic-y, energetic-y after this, and that has to do with like enzyme inhibitors. But largely the rest of the course is going to be mechanisms and it's going to be building on that. And so I really wanted to make sure that we all get kind of on the same page for these foundational topics, which are molecular orbital theory and CAD reactions. And I'll talk a little bit more about it then. Then from there, once we're in reactions land, we'll do the spartyl proteases first. And then after that, we will jump over and talk about enzymes. First with Michaelis-Menten and kinetics, and then with enzyme energetics, which is basically the reaction coordinate diagrams, which I like to think of as like the roller coaster maker for chemistry, I guess. Like, you know, I'm forgetting the name of the game, but there's this like old PC game where you like build roller coasters and you can send your little people up into the sky and then they like fall off or whatever. But that's energetics to me. I know what game you're talk. Yes, I'm sure you do, but I'm like, what is? I forgot it's the name of it. It's probably like roller coaster maker or something. But anyway, that's the general game plan. But before we jump into that in content, are there any like logistic questions, anything that came up this week? Are there any thoughts and feelings about the problem set? The first one should be probably graded and given back maybe Thursday, is what I'm thinking. I don't control that. I'm just guessing. It's probably going to be Thursday. But yeah, any logistic questions, either feel free to unmute and ask or put in the chat. Slay. Oh. Also, are we like 2 weeks out from the first exam? Like 2.5? Because I think it's like we do 3 lectures and then the exam. We have class 4 and then exams after that. So yeah, our first exam's on the 26th. Cool. We're going to be fine. We got this. So let's start out with some foundations and review. So this is primarily for anyone who did not take Chem 17 last semester. So I'm talking specifically to my I've taken OChem 1 at another institution folks, or the it's been a minute since I've done organic chemistry. And I'm going to start off with molecular orbital theory, which is really the kind of foundation of how we teach organic chemistry at Harvard. And molecular orbital theory focuses on how reactions happen by talking about the molecular orbitals. So atomic orbitals, we're thinking like S and P and sp2 and all this. And molecular orbitals, really we're referring to kind of our bonds and then the things that are non-bonding. So we have our sigma bond, and remember sigma bonds are head-to-head overlap of orbitals where there's like actual direct overlap of the orbital from this guy and the orbital from this guy line up in phase. Then we have pi bonds. Remember, pi bonds are only with p orbitals. And this is our kind of side-by-side overlap of like, we are neighbors, and then if we are in phase, we can spread out. And oftentimes, we will write this as like, this becomes kind of a big loaf, and this becomes a big loaf. And we shade one of them to show this idea of phases, of like a positive phase, negative phase. It's not like positive and negative charge. It's more kind of like, you know how you have a wave, it's like above the middle and below the middle, but honestly it's like above our pay grade right now. So we have sigma bonds, pi bonds, and then we have non-bonding, which we typically abbreviate with N, or sometimes NB. And this is like lone pairs is an important non-bonding molecular orbital. So a lone pair on oxygen, we might just write N with a subscript O to be like it's a lone pair on oxygen. Or for like a carbocation, which you saw in like SN1 mechanisms in OChem 1, we would say like N, non-bonding, and carbon. So importantly, all of these that we've seen so far, pi, sigma, and lone pair, not the carbocation, but all of these are orbitals that are filled with electrons. Carbocations notably are an empty orbital, an empty p orbital. But the first kind of key idea of molecular orbital theory is for every bonding molecular orbital, we also have an anti-bonding molecular orbital. So this idea, I want to go back to that idea of waves. So if you've taken a physics class that talked about waves, one concept there is called wave interference. And so it's about what happens when you overlap two waves. And sometimes they can combine in a way that amplifies the wave, and we call that constructive interference. And sometimes, if they are kind of out of phase when they line up, then they can completely cancel out, which we call destructive interference. And why are we talking about waves when we are really supposed to be talking about like chemistry, electrons, all this? Well, remember, it goes back to this idea that electrons are partially particle-like and partially wave-like. So they have some properties that behave like this. So if we've had our sigma bond, our pi bond, and our non-bonding, and specifically our sigma and pi bond because those are bonding molecular orbitals, what do those antibonds look like? So the antibond here is, instead of putting our big lobes in the middle for our overlap, our big lobes go on the outside for a sigma bond, and then our shading is off. Like one of them shaded, one of them's unshaded, and it creates a little node. Right now, you don't need to worry too much about drawing these, but I do want you to get an idea for like the kind of geometry of what is going on, and we're going to put this into practice immediately after this. So I'll let you see the kind of relevance in a minute. Again, and we're starting out with the non-polar bond here. We just kind of flip these orbitals around, and then we get our antibond for sigma. For pi, we go from having them both shaded to having one shaded up top, one shaded on the bottom, and that creates a node in between it as well. It gets a little weird with polar bonds, though. So in non-polar bonds, the atoms are sharing the electrons totally evenly. But our polar bonds is, imagine we use that kind of loaf metaphor here. So this would be a pi bond, which is made up of a p orbital and a p orbital. But oxygen's more electronegative. We have a dipole that is going this way, and the electrons are going more towards the O. And so our loaf kind of gets a little chunkier towards the O and a little bit slimmer towards the carbon to show that the electrons are more attracted to the O. Similarly, in a sigma bond between carbon and chlorine, instead of just being like a neutral loaf in the middle, it's going to be kind of more towards the chlorine and a little bit less towards the carbon. So this feels like a lot of like niche detail, and also something that you can be like, ah yes, there are more electrons around more electronegative things. Groundbreaking. But it's kind of weird for the antibonding orbital. So on the antibonding orbital, we need to compensate for that unevenness. And so for the bonding interactions, we have the larger lobe on the more electronegative element. But for the antibonding orbitals, we put our larger lobes on the less electronegative element. So here, for a CO pi bond, the pi star, which that's how we indicate an antibond with this little star. The antibonding for a CO pi bond puts large lobes on the carbon. So let's use this, like, and I wrote these as the upshots of like, our bonding MOs are filled. And the other idea is antibonding molecular orbitals that we have here, these do not have any electrons in them. And that's going to be a really important idea. All of our electrons are where we can see them in the bonds. So what are these antibonds doing? Why do we care? That kind of brings me here to the second idea. Electrons being put into antibonds make the bond break. Now, in my like OChem 1 class, I like have us chant it in like a Pavlovian conditioning style, like the girls walking in the forest and going, Camp Rock, Camp Rock, of like, this should be so internalized. Electrons in, antibonds make the bond break. Can we just to ourselves one more time chant through it together? 5, 6, 7, 8. Electrons in, antibonds make the bond break. Woo! So let's see how that manifests. So we'll start off with an SN2 reaction. Granted, this isn't a great SN2 reaction, but there's a reason for it. So if we had an attack here on this carbon, you all have probably written these arrows in OChem 1. We attack the carbon, and then we kick off this iodine as a leaving group. But what are the actual MOs involved? Well, the thing that's attacking is a lone pair on the oxygen, and we have to put our electrons into an empty orbital. So what is that orbital? Well, let's look. Did we break a bond in this process? Heck yeah, we broke this sigma Ci bond. So if we broke this sigma Ci bond, where did we put electrons? We put it in the sigma star Ci, the anti-bond between carbon and iodine. And that's also why over here we said in a polar bond with carbon, we attack the carbon because it has the larger lobe here. It both has a larger lobe, so it's easier to attack, and also it has more of a partial positive, so there's kind of a dipole reason. So SN2 is one example here, where we broke this sigma bond, so we must have put electrons in the antibond. Okay. For carbonyls, which some of you who've done OChem 1 at other places have not seen carbonyl reactions before this, the bond that we are breaking is the pi bond between CO. So we know that because we broke that bond, we put electrons in the anti-bonding CO pi bond, so the pi star CO. And here, the thing that did the attack again was a lone pair on oxygen. The other idea to remember with curved arrows is just that each arrow has a consequence. So where did the electrons that went and did this attack go? Well, they became the bond between carbon and the oxygen that was in the H2O. Where did the electrons in this bond go? They went and became a lone pair on the iodine. So just reminding of all that housekeeping. But, okay, so we have the idea of there are these antibonds. When we put electrons in the antibonds, we break bonds. So the next big idea is like the energy levels of these molecular orbitals are really critical for the reactivity. So generally speaking, we say that bonding orbitals are low in energy, anti-bonding orbitals are high in energy because they have those nodes, they don't want to exist. And then in the middle are non-bonding orbitals. And specifically, sigma is lower in energy than pi, then we have non-bonding pi star, sigma star. So whenever we have a reaction, there's going to be some sort of donor and some sort of an acceptor. And there will be a gap in energy between this donor and acceptor. And that gap in energy affects the speed of the reaction. It's really directly tied to activation energy, actually. So this will tie back in when we talk about the energetics later. You might have also heard this called the HOMO-LUMO gap if you've done some MO theory before. But if this is the thing that limits the rate of a reaction, having a big gap between donor and acceptor, we essentially have two big strategies for how to make things faster. We can raise the energy of the donor, and then we get a smaller gap. Or we can lower the energy of the acceptor to get a smaller gap. That seems fairly intuitive. But one note here with this energy of a molecular orbital, that does not always equal stability. So, for example, a high energy donor is more reactive. That kind of makes sense. But with acceptors, it's flipped. A low energy acceptor is the one that's more reactive. And so it's not about stability for being reactive as a electron acceptor. It's about reactivity. And when we lower the energy level of our acceptor, we make it more reactive. So we'll keep that in mind as we look at this example at the bottom. But also just like a really quick recap of terms. The molecule in a reaction that donates, we call the nucleophile. And the molecule that accepts electrons, we call the electrophile. And then I made a list here of some good donors. So our number one for good donors are lone pairs, followed by alkenes are good donors. And then our good acceptors, we love a carbocation, we love an empty orbital and a boron. We love pi stars, so like carbonyl, like the anti-bonding for the carbonyl. And then we also like anti-bonding orbitals between carbon and something that's electronegative. So if we think about these two strategies making reactions better, over here I had water attacking ethyl iodine, and I had water attacking acetone. Well, if I wanted to make this reaction better, one thing I could do is I could raise the energy of the donor. I gave the donor a negative charge. We have a buildup of electrons. It really wants to donate. It really wants to attack because you have a buildup of a negative charge. And then it's going to make the rate of this reaction faster. So we made a high energy donor. For this reaction, I kept my water, but I protonated the carbonyl. And that made this a much better electrophile. And so this water can go and attack it. So the positive charge makes it a better acceptor. And this is the weird thing. We lowered the energy of the LUMO, or of the accepting orbital. And by lowering that energy, we made it more reactive. So if you see a protonated carbonyl and you're like, that's really reactive, she now has a charge, it's like, yes, it's more reactive, so it's lower in energy for the antibond. It's kind of confusing. But this is like a brief introduction to MO theory. The biggest thing that you need to be able to do at this point is when you are doing curved arrows, you need to be able to identify this kind of stuff. What is our donor orbital? What's our accepting orbital? Because we are not doing a lot of it in class now, but it will come back later, and there will be some orbital like requirements that come back. And I just don't want people to be blindsided when that come up. So any questions on MO theory before we talk about CAD reactions? I know that was kind of a lot. Oh.
Can I ask a quick question about stability?
Sure, please.
So you said that the high energy donor is less stable and the low energy acceptor is less stable.
Yes.
Should we okay.
And it's like less stable equaling more reactive, kind of. Like that's the bigger thing. And it's not always that higher energy is more reactive. That's kind of our typical association that we have, but it's flipped with acceptors, essentially.
Okay, got it. Thank you.
Yeah, totally. Cool. Okay, from here, let's talk about CAD reactions. So what do I mean when I say CAD? CAD is our abbreviation for carboxylic acid derivatives. Carboxylic acid derivatives are a family of functional groups where we have a carbonyl, C double bond O, and essentially we have something interesting on one side. So carboxylic acid, we have an OH. An ester, we have essentially an ether on the other side. We have like an OMe, something like that. An anhydride, we have an O and another carbonyl. Acid chloride, we have a Cl. Amides, we have nitrogen, so on and so forth. And in CAD reactions, one of the biggest thing that's important is thinking about how reactive our carbonyl is. So the reactivity of our carbonyl depends on the resonance that we have. So let's start at the least reactive. Our carboxylate here, when we do our resonance structure is virtually identical. We have the same charges on the same types of atoms or the same elements. And so these are equally stable resonance structures. This is not going to be very reactive because it's pretty stable. And then as we go up, I'm not going to go through all of them. This is more of kind of a reference here. We see that for carboxylic acid, it has resonance, but there are charges, a negative charge and a positive charge. So this is going from neutral to two charges, which is not as good. And there's a positive charge on an oxygen, but still there is some stability from having that resonance, but way less than the carboxylate. And then as we go up to something like an acid chlorides we fully say are just unstable. And a lot of it is because this resonance structure is really kind of crappy. And it's crappy because even though we could do arrows, we could donate from the chlorine, push up to the carbonyl, this chlorine is on a different row of the periodic table, and so she is much bigger. So it's just like a size overlap issue here of like the chlorine's p orbital is much bigger than the carbon's. So this is not a very stabilizing resonance structure, so this is more reactive. We have this carbonyl here that we can attack more readily. All of these carboxylic acid derivatives, you don't need to know a bunch of reactions for this because we're going to teach it as it comes up in biological context. But generally speaking, these are going to be acting as acceptors, and our accepting orbital is going to be the pi star CO. So essentially what we are going to do is we are going to attack carbonyls and push up. And remember, we are putting electrons in the anti-bonding CO, and so we have to have a consequence arrow where we break that bond. Cool. The core reaction that happens in all of this families of reactions, the CAD family of reactions are going from like one of these functional groups to another. And if you did a whole unit on it, you would talk about how it's easier to go down in reactivity from like an acid chloride to any of these other guys than it is to go up. Going up is a little bit harder. But the core reaction for all of these is the same. We can think about the interesting thing on the molecule as a leaving group. What do you think a leaving group does? It leaves. So the mechanism here is some nucleophile comes and attacks the carbonyl, pushes up. So that's our first step, this carbonyl attack. And then we are going to do this thing that we call a lone pair push and kick off our leaving group. So LPP is lone pair push. And I'll talk about that a little bit more later. But we are just going to reform our carbonyl and kick off this leaving guy. And then now we have a new functional group. So that's kind of the core idea. But these strategies that we saw here of like raising the energy of the donor, lowering the energy of the acceptor, we see a lot in these CAD reactions, and we're going to see a lot in biochemistry. We see it in the proteases. So just for one example, this is not a mechanism where you need to worry about writing out all the details and all of this. Like it's literally just to demonstrate a point, and then we're going to see it in action in just a minute with the spartal proteases. But for esters, we can turn an ester into a carboxylic acid in two ways. We could do it with acid, or we could do it with base and have a final step that's like a little acid workup. And so I want to talk through the strategy that doing this in acid and base like takes. Like why do we do it in acid? Why can't we just add water and have it happen? Well, so the mechanism here in acid, when we are in this really strong acid, what we do is we protonate the carbonyl first. Then we have our core attack the carbonyl step. So I said that this is the kind of core reaction here, and every other step is basically just going to be some acid-base stuff. So we had this first protonation step, and then we had our core part number one of we attacked the carbonyl. Now, water, is she a good nucleophile? Is she super reactive? No, she's water. We drink her. We are made of her. So if we have a crappy nucleophile, we want to have a better electrophile to make up for that. Like, it's essentially the case of, like, I don't know, like an autosomal recessive gene of, like, if we're a heterozygote, if we have one good and one bad, we're safe. If we're both bad, our reaction just won't proceed. So, now that we have a good acceptor with this protonated carbonyl, water can attack. We do a little proton transfer here where we remove a hydrogen over here and add one over here. And then we do our second core step, the lone pair push, and kick off this HOME as a leaving group. We have a final deprotonation, then we're done. So the big thing here, why did we protonate? One was electrostatics. When we protonate this carbonyl, it is making this oxygen really want electrons. And so we already had a dipole in place before. But after we protonate the carbonyl, we have a much bigger dipole. And so there's a bigger partial positive on that carbon. And so it wants electrons. It's going to, like electrostatics, positive and negative opposites attract. It's going to pull on that more. And then we are also lowering the energy of our pi star CO acceptor orbital, that MO theory that we were talking about earlier. Okay, so that's the kind of strategy in acid. We make a better electrophile, a better acceptor. But in base, we could just straight up go and attack. If we have OH minus, OH minus is a great nucleophile. So even if we have a kind of crappy electrophile of just a plain Jane carbonyl, it doesn't matter. We have one good one, so we can attack. Okay, then here we can directly do a lone pair push and kick it off. And these final steps that we have to do in this reaction are literally just, we made a carboxylic acid, and we said that we're in base. And so we definitely have to deprotonate this because we are in base. And then we do a little final acid workup step to get back to the product carboxylic acid, which I don't think I actually wrote out. So I will write out here. So why could we just attack in base? One of it's electrostatics, but the flip of what we saw before. The negative on the O means that there's a larger buildup of electron density, so it wants to share electrons really badly. It wants to find a partial positive and make a bond. In MO theory, we raise the energy of the donor to lower that donor-acceptor gap. Okay, so we've seen acid strategy make a better electrophile, base strategy make a better nucleophile. In lab, we have to pick one. We have to be acid or base. But in enzymes, we can have it all. This is biochemistry. I feel very Theranos biochem of like, wow, the future is now. We can do all the things. So this is our aspartyl protease. So who is she? Aspartyl protease, interstage left. A protease, something that chops the amide bonds between amino acids in a protein. And aspartyl, we have two aspartate residues in our active site. So that's going to be kind of the setup here. And the strategy that the aspartyl protease uses is we are going to make both a good nucleophile and a good electrophile using acid-base chemistry. So in our active site, we have the peptide sequence that we are going to try to chop up. And specifically, I'm like in green here, I have the amide bond that we're going to try to break. And we have two aspartate residues or aspartic acid residues. One of them is going to be in base form, so it's going to have a negative charge. And one of them is going to be in acid form and still have its H. And we'll talk about why in a little bit. But let's see what we do. So I'm going to show the unabbreviated kind of first chunk. And what we do is we protonate the carbonyl to make it a better electrophile, a protonated carbonyl. That's what we did in acid in the lab. Okay, and then with our basic aspartate, we deprotonate water to make it a better nucleophile. Oh my goodness. So instead of just having like one good one, one bad one, we now, biochemistry-wise, can have a great nucleophile and a great electrophile. Isn't everything great? So the second step after we've done this kind of setup, making our good electrophile, good nucleophile, is we do that core step that's at every CAD reaction. We attack the carbonyl. And then at the end, we have this tetrahedral intermediate where we have 4 things on it. So this already is a lot to write, you know? And so we have an abbreviation for this mechanism, and it puts all of this into this one step. So what we do is we show the formation of this O- by going ahead and doing this deprotonation. And instead of going to the oxygen, we are going to directly use that to go and attack the carbonyl. So it's like we're combining the base arrows here, and then we are having the carbonyl attack arrows, which are here in purple. And then finally, we are also doing that protonating the carbonyl. And again, that's one of the first things that happen. Technically, the order is we do these two things first, then we do the purple stuff. But we are saying, hey, you can just show it the whole time. So slay. That saves us a lot of time and a lot of writing. Okay. Well, let's see what happens after that. So we got to this intermediate where we had 2 OHs on here. And fundamentally, remember for our CAD reaction, we have the carbonyl attack phase. That's done. That's successful. And now we need to kick off a leaving group. So I'm going to give you like my take on lone pair pushes kicking off leaving groups. So I imagine a tetrahedral intermediate like this, where we have 4 things on it, specifically right after we've attached a carbonyl, as a apartment that has 4 roommates living in it. And the setup for the lone pair push is someone gets really, really annoyed and kicks one of the apartment mates out. And like literally pushes them out. One of the Ochem professors at Harvard describes the lone pair push as a cinematic moment. Like it's drama, it's tea. It's like, oh, did you hear the newest gossip about my roommate drama? And we have the idea that some things are better lone pair pushers than others. So in a SpongeBob metaphor here, a kind of neutral Squidward would be this OH. OH could do a lone pair push, like we could just push in here, but it's neutral, and so it's not going to be that strong of a lone pair pusher. Whereas if we deprotonate that OH and make an O-, now we're pissed off Squidward. Now we are ready to kick things out. We have a buildup of negative charge. We really want to make a bond and get our annoying thing out of here. Now, annoying thing, the other part that we have with this situation is the leaving group, the thing that's going to leave. And right now, this NH part of the molecule does not want to leave. Because if it just left as is, if we lone pair pushed off here, we would have NH-. We'd have a nitrogen with a minus charge, which we rarely see. It's like pretty darn unstable. And so this nitrogen right now, she is comfy, she doesn't want to leave. But if we can protonate this, it's kind of like packing its bags for it. So if we protonate this and make it NH2 plus attached, then when it leaves, it becomes this neutral NH2, which is stable on its own. Great, we love to see it. And so when we make something a better leaving group, I like to say it's like we are packing its bags before we kick it out. So we went from having a bad lone pair pusher on this intermediate, and we went from having a bad leaving group, this neutral thing, to, if we do some acid-base chemistry, making it a great lone pair pusher and a great leaving group. So let's see how that's abbreviated over here. So to make our better lone pair pusher, we deprotonate up top here. And one kind of cool feature is we initially saw this aspartate act as an acid. It gave up a hydrogen. But now, role reversal, she's acting as a base. So she is doing this arrow in blue, taking a hydrogen. And then we take the electrons from that and start to do our lone pair push. And so our lone pair push, we would push in, make a carbonyl, and we would kick off our leaving group. But remember, we need to make it a better leaving group when we kick it off. And so we're going to have this combine with our acid step and grab a hydrogen off of this bottom aspartate, which originally was a base, but now is acting as an acid. So this is our way of, like, I showed kind of the steps explicitly here, but I just abbreviated the aspartals as a general base, general acid. But we can combine it all in one. And then what we are left with is we have, after this lone pair push, we have an OH over here, carboxylic acid, and we have an NH2, an amine. But at physiological pH, we know that this is going to become negative charge, this is going to become positive charge. And so there's one final step here where we do a deprotonation and a protonation, or we do acid-base chemistry, basically. And that makes us our physiological pH charges that we want. And so, to not have to write all of this out, we can use the abbreviation proton transfer, PT. So if you write that over this arrow, then you can just go directly to the charges of that we have at physiological pH here. You don't need to do an extra step. And so, like, the unabbreviated form would be writing all of this and all of this with even more detail because I abbreviated a lot. And the abbreviated form makes this 2 steps of arrows and a product. Love this. Love the abbreviations. It might feel a little bit weird right now at the start, but you will also come to love the abbreviations because they make your life so much easier. And we're going to see a lot more of these kind of abbreviated biochem mechanisms. Importantly, at the end of the day, we've reset our active site. So our acid is an acid once again for the aspartic acid, and the base is a base again for this bottom aspartate residue. So, questions about this mechanism are kind of how we tied our MO strategies of like raising the energy of our donor, lower the energy of our acceptor, acid-base strategies that we saw in the lab to the aspartyl proteases. We're now doing all of it together. We're making good electrophiles and good donors. Or any other questions here connected to the aspartyl proteases? My little section snack for today is Trader Joe's animal crackers. However, I had one a minute ago. I was like, these are kind of stale. So, I need to get a better section snack. But, okay. So, maybe if, love Trader Joe's. Love Trader Joe's, all the things. I actually don't get real food there, though. I only get snacks. So, it's my snack destination. But, okay. So if there are no content questions on this, I have a content question for you. And don't just scroll and see the answer. Why are we able to do this? Because in a lab, we're in a beaker, right? And so in a beaker, we just have to set the pH in our beaker and make it either a base or an acid, but not both. But here, we are having steps where an acid and a base are coexisting only like... I was going to say only feet from each other, but like scale that down to molecules. Only angstroms from each other. Like how can we have both an acid and a base in the same vicinity? Like normally we would expect to see a carbonyl like this. So there must be something happening in an enzyme that's special that we can't recreate in a beaker in like just normal OChem. So that idea here, I like to think about it as like the TikTok algorithm, like getting really, really specific and generating like your For You page versus someone else's For You page. Y'all are living in different spheres. You're on different sides of TikTok. We call this, like on the chemistry side of it, the microscopic pKa. And so it's about how the local environment of a hydrogen tunes the pKa of a specific proton. So, for example, and this is what we saw in one of the questions from lecture, if our carboxylic acid is surrounded by a bunch of non-polar things, it's not really safe for it to be a negative charge. This negative charge doesn't have anything to hydrogen bond with and is not very stable when you're surrounded by non-polar things. It's not going to fit in here. And so, if you are surrounded by these nonpolar residues, you can't really form the negative really well. It means you don't want to lose your hydrogen, so you're less acidic, which means you have a higher pKa. So this one has a pKa of about 6.5, which is higher than the value that we have on your like printout of the amino acid pKas. Whereas this aspartate residue, surrounded by a bunch of polar things, she can do hydrogen bonding and have electrostatic interactions. And so this O with a negative charge is pretty darn stable. It's safe for that negative to exist because of these like electrostatic interactions that we have broadly. And so this molecule can readily give up its hydrogen and go from the carboxylic acid form to the carboxylate form. So if it can give up its hydrogen easy, it's more acidic, we have a lower pKa. So that's kind of the reasoning behind this. The microenvironment around our residues can fine-tune that pKa and allow us to have bases and acids in the same enzyme or in the same active site. So, with that, let's do the first big practice question. So, to be so honest, I gloss my eyes over a little bit every time I read question prompts for biochem, which, like, much love to the folks who created it. I'm like, great, this is related to ACE inhibitors, which are like drugs that you can take that like affect your blood pressure. But we don't need to know anything about that to answer this. And so I'm gonna like skim it and give you my reading of this. This hormone thing, sodium, we have a protein, love proteins, undergoes peptide bond cleavage by an aspartyl protease known as renin, which, important, cleaves on the C-terminal side of leucine 10. Okay. So, the resulting fragments released, whatever. A. Provide the curved arrow mechanism to go from angiotensin to angiotensin 1. Or from angiotensinogen to angiotensin 1. Okay. So basically we need to do the aspartyl protease mechanism that does this cleavage. To go from the big protein that's 453 residues to chopping off a fragment and making this like smaller angiotensin 1. So let's first figure out where we're chopping. So when we have this like number by a residue, that is our number amino acid that we are in the sequence when we start the N-terminal side. So, like this is ASP1, ARG2, Val3, tyrosine 4, 5, 6, 7, 8, 9, 10. So this is leucine 10. And they've told us that we are going to cleave on the C-terminal side. So if this is the N-terminal side, we are going to cleave here on the C-terminal side. Because we always write our proteins N to C. And that's just a convention that we use as a class, and that most people use. But, okay, so it says you may abbreviate everything more than one amino acid away from the sissyl bond. Fancy word for the bond that we are going to cut. So, let me start by just like drawing that leucine. So, I want it to be consistent with before, so I'm like, do I do it up or down? I'm going to do it down. So, let's do NH. Then we're going to have our down leucine. And leucine, again, I remember, is like a tall V, so it's like one carbon, and then you have your V. Whereas if it was valine, we would split off right here and have our V. Okay. So we have our alpha carbon there, then we're going to put a carbonyl, then we have our NH, then we have another residue, which the one after leucine should be valine. So we're going to do, remember if we are on a peak, we put on a wedge, and then our V splits there instead of leucine long V. And then we can stop everything that's more than one amino acid residue away from the bond that we are breaking. So like this is the bond that we are breaking, and I believe that we can cut it off here on both sides. I'm just checking. They want us to put the other carbonyl here, but like roughly we want to be able to see, this looks like an amino acid shaped thing, and then after we cut this will look like an amino acid shaped thing. So that's kind of step one of like draw the peptide fragment that we care about and like highlight the bond that we are actually trying to break. Okay, so we have our peptide. What else do we need in the active site? Well, we need our acid, aspartic acid up here, up top. we need our water. And down bottom, we need our basic aspartate. And so, with this, we start drawing the mechanism. So I'm gonna make this black. And I'll ask this because it is a little bit more work, but sometimes I think it's helpful. I can either just do all the arrows in red, and so the arrows stand out, or is it helpful to do this color coding of like the base thing here in blue, the acid thing in red, the attack here in purple? Like, is the color coding helpful here, or is it distracting, or like, are y'all neutral? What do people think? Okay. Neutral to positive. Work. I'm glad that no one's like, honestly, it's the most distracting thing in the world. This is the reason why I hate chemistry. So, as long as we don't have that, I'm good. But yeah, okay, I can do the little color coding. So, remember, we need to make this a better nucleophile, we need to make this a better electrophile, and we need to have the attack happen. So, I'll start off with making a better nucleophile. We're going to deprotonate the H on here. And then instead of going to the oxygen, we are going to start our attack of our carbonyl. And here, we're going from the electrons that are in this bond, which really, remember in the unabbreviated, it's going to be a lone pair. And we are attacking our anti-bonding pi orbital here, which is empty. If we put electrons in that anti-bonding orbital, we have to break the bond. So those are our purple arrows of the carbonyl attack. I'll also label this step as the carbonyl attack. Then we have to do the acid steps to make this a better electrophile. So a lone pair on our oxygen needs to go up and grab a hydrogen and then give the electrons in that bond back to the aspartate. So now, they told y'all to not copy and paste, and I love that for y'all. And I'll say it that way. I am gonna copy and paste because I've already done my time. When I actually took Chem 27, I wrote it out. Actually, no, that's a lie. I didn't. I just like said, you know, time's gonna be rough on the exam. Time is rough a lot of the time. So, again, do as I say, not as I do. And then, big things, we need to make sure our changes are felt here. So, we protonated this bottom aspartate, so it should have its hydrogen on it. We deprotonated the top one, so it should have a negative charge. And remember, we have some hydrogen bonds going on here that help to kind of stabilize this transition state. And so that's nice. It kind of helps hold the molecule together here for this intermediate. And this is the one where we need to do our big step 2, which is lone pair push off the leaving group. So first, I'm going to have this top thing act as a base and remove the hydrogen here in order to make this a better lone pair pusher. Okay, so then the electrons in that bond, instead of just going back to the oxygen, we are going to lone pair push down to create a pi bond here. And when we do that, we are going to kick off the nitrogen. Now, we need to make this nitrogen a better leaving group at the same time for this whole kind of abbreviated step. And so, the other thing that we need to do is we need to protonate it. So that arrow is going to start to do some acid stuff. It's going to take that hydrogen and then give the electrons in that bond back to the bottom aspartate. And so then, remember, these are our 2 core steps: carbonyl attack, lone pair push off the leaving group. So now we can just draw our products. So our products, we had our NH, we had our Lucy, and then here, if we put a PT over the arrow here, we are able to go from, normally we would still have an OH on here, but we are able to go immediately to the O-, which we want. And then, consequently, on the other side, the nitrogen, which is attached to all this, that nitrogen we want to have a positive charge, NH3+. Proton transfer lets us do that. So we have our 2 core steps, and then the little proton transfer at the end. So one thing I personally like a lot, I should draw, the aspartate residues. So on the top, we've reset the acid, and on the bottom, we've reset the base. So hashtag reset. And now these things can exit, and then another peptide bond, another water can come in, and we can do it all over again and again and again and be our little protein machine. So one thing I really like about this abbreviation, even if it does take a little while to get used to the ins and outs of it, is, remember we said this was the core reaction for like the CAD reactions, for any like converting between carboxylic acid derivatives. But this has 2 steps, and the real reactions in acid and base, so many steps. My gosh, why are we at step 4 or 5? What are we doing? Like, there are 2 core things that need to happen: attack a carbonyl, lone pair push off the leaving group. But then we had to do all this acid-base stuff. And with our abbreviation, we kind of get back to that core reaction. The carbonyl attacking is one big step, and we fold in the acid-base stuff. And then the lone pair push off the leaving group is one big step, and we fold in the acid-base stuff, and we're done. And so we're really kind of getting back to, like, what's the big idea of the reactivity here? And we are aligning some of the detail work to make the big idea clearer. Yeah. So, any questions on what we did on the aspartyl protease? That's all I really have for y'all on mechanisms before we go over and talk about kinetics and energetics. As we are also pausing, I can't help but ask for feedback, because this is the first time I'm doing this. Was the MO theory and CAD review too much at the start? Was most of that like, I know this, I didn't really need all this, only the aspartyl protease stuff was new? Was it helpful to see some of it? Did I lose you in the foundations? Yeah. Any feedback? Yes, on the first section before we go into new stuff. Okay. Yeah, and again, all this MO theory CAD stuff, we're not going to explicitly test you on this. I think most of it's like background context, especially if you've never seen it before. It was just kind of like to orient you rather than like tossing you in the pool. Okay, cool. Generally positive vibes of like, cool. Yeah, so do not worry about these mechanisms at all. Remember, you don't learn any new content in section. We are only reinforcing lecture. But I thought that lecture could be reinforced by some concept, or from some background kind of things, some context. Okay, with that, let's do a hard switching of gears. We are no longer in curved arrow lands. We're actually in like chemistry is graphs and math and stuff. Which is my less favorite form of chemistry. But, generally speaking, we want to know how enzymes are impacting the rate of a reaction. And this is Michaelis-Menten kinetics. It's essentially, in Gen Chem you have a big kinetics unit where you do 0th order, 1st order, 2nd order, and you learn a bunch of graphs and the integrated rate laws, blah, blah, blah. It's like, what's the biochem version of that? How do we talk about speed with enzymes? So I want to talk a little bit about the foundations of this curve. And a lot of this is just kind of like, again, giving you some like more kind of context on who she is. And then we'll do reading a curve. And the reading the curve, honestly, I don't think is that hard. There are like 2 things to pay attention to and you're done. But why do we do this? So like we say that the curve here, if we plot the substrate concentration and the reaction speed here, the curve for a catalyzed reaction with an enzyme does this shape here, which we call a hyperbolic shape. But just for context, what does it look like if we don't have an enzyme? So if we don't have an enzyme, it would look like this. So, 1, it would be linear. The more substrate we added, the faster we would go. Because we don't have any enzyme to worry about. We're just kind of like throwing more gas on the fire and eventually it'll go. But it's relatively slow. So it doesn't even get to like half of the speed that we get for the catalyzed reaction. So uncatalyzed, it's slower, but it is linear. So more substrate added, faster it goes. Well, when we are in the enzyme version, the catalyzed version, it starts off and it looks kind of linear at the beginning, but then it starts to level out. So what's happening? I like to think about this as kind of like, the like board game Life and like the little cars and you put the little people in the cars. So imagine the enzymes are the little cars and the people are the substrates. And let's say we start off and we have a substrate concentration that's 4 dudes here. And I'm just going to put 1 into each car. So if our initial substrate concentration, which I'm calling S1 here, is 4 people, and we have this many enzymes, a fixed amount of enzymes, then great, we are doing more of the reaction. So as we go up from S1 to S2, we are putting more substrate into the enzymes, and hey, more reactions happening. We're getting faster. Then if I add these guys, wow, we're getting faster. More substrate into more enzyme. Adding these, same thing. But then when I go to add these, all the enzymes taken up. And so adding this more substrate is not going to speed it up further because all of the enzyme is taken up doing more reactions. So actually, this substrate has to wait in line. It has to start queuing. And then if we add even more substrate, it's waiting in line. It's not making things faster. And so that is kind of what's happening here when we are leveling off. We are reaching this kind of steady state where all of the enzyme is being satisfied by substrate. And so adding more substrate is not going to make it faster. And so, whereas for uncatalyzed, this will go on kind of to infinity and get as fast as you want it to be. This, we approach kind of a maximum speed that we can get of an enzyme. And that kind of makes sense of like, if you think of enzyme as like a little factory worker, like it does its one job in the assembly line of like, I cut peptide bonds over and over, or like, I make bioesters or whatever. It does a one job over and over, and it's not going to get like infinitely fast. It's like, this is a person, it's going to get tired. Yeah. So, yes. I have a side note here that honestly, I'm probably not going to go into much detail about. But one thing that might have thrown y'all off when you saw it here is when we did this in section or in lecture, we call this V naught, which means the initial velocity. And just very briefly, it has to do with where did these points come from? How did we go from solute concentration to speed? And where it came from was by plotting how much product appears over time. So if we had this much substrate, 2 micromolar, then we would make this much product over time. And then it would kind of slow down Same with making product over here and over here. And again, it levels off, but initially, at the very beginning, it looks really linear. It looks like lines. And so what we did to get those points were we took the solute concentration and we took whatever the slope was at the very beginning, the initial velocity, and that became the thing that we were plotting. We were plotting these initial velocities of like this versus this versus this. And velocity here is the slope of these lines, the change in product over change in time. And so, again, you don't need to know this. It's just kind of like if you were thrown by why are we talking about initial velocities, V naught, this is why. It comes from the data that we're collecting. You can literally just think of it as speed. You don't need to think about like, oh, we're plotting all of this or anything. And that's why when I showed it here, I just wrote it as speed, because that's functionally what we're treating it as. So that's kind of like the setup of this, of like, why is she shaped like that? We're filling up all the enzymes and everything. So what do you functionally need to be able to do with these things? Valid question. You need to be able to notice two key features for a Michaelis-Menten curve. The first feature is Vmax and like connected half of Vmax. So if we consider this as our main Michaelis-Menten curve, the asymptote up top that it approaches is Vmax, the maximum velocity that you can get to. Okay, if that number is 100, then half of Vmax is literally half of that. So you literally just go like halfway down the line, you try to split this into two. Great. So that is the first thing that you need to be able to notice, Vmax and half Vmax. The second thing that you need to notice is if you go from that half Vmax line over and hit the curve, and then look at what is the solute concentration, or substrate concentration, sorry, associated with that, that is this thing that we call the Km. So, the Km is the Michaelis constant, and this isn't the real definition of it, but it is a functional definition that will get you through the day. And we don't make y'all do all of the math for Michaelis-Menten in this class. Some classes are very math heavy with it. So we can think of Km, the Michaelis constant, as literally by definition, this definition, the substrate concentration, remember on our x-axis substrate concentration, that produces an enzyme velocity of half Vmax. And this property is going to be constant for any given enzyme at a specific temperature. So, cool. We can find Km by going to half Vmax and then seeing the substrate concentration that intersects with that. So, one thing to be thinking about is like, what does it mean when we have a big Km? Or what does it mean when we have a small Km? So a big Km means that we need a lot of substrate to get to half of Vmax. And so functionally, it is like we're kind of shifting the curve a little bit to the right, or making it a little bit more broad. Instead of needing, let's call this 10 molar, instead of needing 10 molar, we might need 20 molar, a much bigger solute concentration in order to get to half of our speed. And so what are some reasons why we might have a big Km? And again, these are options, these are possibilities, which is why I put question marks. It is not the way, the truth, and the light. Amen. So one reason why we might have a big Km is the reaction just could be slower. And so, like, it could take up more enzymes, like they're not turning over the products as fast. It could be that there's low binding affinity, that our substrate doesn't bind very well to the enzyme, and so you need more substrate in order to actually get the same kind of binding and same rate of reaction. There also could be an inhibitor present, like a competitive inhibitor. So those are some reasons why we might have a larger Km. And then the flip of it's a smaller Km. Smaller Km, we need even less substrate concentration to get 50% of Vmax, or half Vmax. So if this was 10, we might only need 5 molar to get to half of Vmax. So this reaction could just be faster, it could have a higher binding affinity, or it could be have like an allosteric activator. Those are just some options to kind of think about why we might have big or small KMs. But KM for an enzyme is typically how we measure like how well binding happens between the substrate and the enzyme. And so it's kind of like a diagnostic tool for us. With that, the last thing here is to touch on the formula. So we are going from enzyme and substrate as separate things to enzyme substrate coming together and becoming the enzyme substrate complex. And we show that with this like dot in the middle. And then technically it goes to enzyme plus product, and then enzyme, or the enzyme product complex, and then enzyme plus product. But that's way faster, so we abbreviate that with just one step. So what Michaelis and Minton did with this setup of how enzymes work is they fit their data to that curve, and they did some math and saw that this is a hyperbolic function. So remember, our V naught, which was on the y-axis, we treat that kind of like a y variable. Our substrate concentration is kind of like an x variable. It's what was on the horizontal axis. And then Km and Vmax, remember, are constants. So our formula that Michaelis and Minton figured out from the data was V naught equals Vmax times S over S plus Km. Which, if we substitute that out for x and y's and make it look more like a math equation, it's y equals ax over x plus b, where a and b are constants. And like this is straight up one of the ways that you can write a hyperbolic function. So again, we're not going to make you do much with this. There were some cool limiting cases in the lecture notes of like, what happens when we have a really big S? Well, if S is really big, Km doesn't matter. So we have Vmax times S over S. Those cancel. So we're at Vmax. Hey, if S is really big, yeah, we're going to be at Vmax. We're going to be at our maximum speed. That makes sense. They're mostly just kind of like reality checks. And to be so honest, I haven't looked at the problem set for the kinetics yet, so I don't think y'all are having to do a lot of math with it. I would be so surprised, honestly. So with that, any questions before we jump into practice number 2? To me, I feel like this is easier than the mechanism stuff. Yeah, like basically we need to be able to locate Vmax and Km, and that's about it. So, practice number 2 here. There's a whole setup. It's connected to the angiotensinogen, whatever, from before. But honestly, look at the question stem. From each substrate, write the estimates of Vmax and Km, and then they give us 3 substrates here. So, yeah, we can do that. That's not going to be bad. So, I'm going to estimate the Vmax for this yellow one here to be, I don't know, 98? Something like that. And the key, they put 95 to 100. So 98 would get full points. So if that's... Oh, and I wrote it in the wrong box, though. So 98, that's our estimate of Vmax. Okay, so what would half Vmax be? Well, it would be 49. So I'm going to go to about 49 over here. 1/2 Vmax. And see, okay, where does that intersect? Golly, that's small. So, if this is 20 to 40, this is going to be 10, that's going to be 5. So, I'm like, are we at 1? Yeah, they put 0 to 4 is acceptable. So, I'm just going to put 1. And we can use units here, so the Km was micromolar here from the axes. And then the Vmax, the rate is nanomole per minute. Cool. So with that, can you all take I don't know, 3 minutes and do it for the orange and the red curve. And I'm going to like leave this up and pause the screen. And then I'm going to write my answer. And then I'll put up the answer. And you can check it and be like, ah, I got the same things. Or you can be like, ah, I called that something different. And I can be like, yep, that's in the accepted range. So you're good. You still have like one more minute, but for the folks watching the video, I forgot that I can't pause my screen, so I've just been silently working. I don't know. If you're hearing this, it's too late. Okay. I'm going to go ahead and share. How'd you do? I would say if you are, for the VMAX, within 5 of what I got, you're good. And if you're within like 2 or 3 of what I got for the KM, you're also good. Cool. Any issues or difficulty on this, or did this feel easier? Okay. Big slay. My backup snack, also from Trader Joe's, are Scandinavian swimmers. And they are slapping. They are really coming in. Cool. So, last topic. Enzyme energetics. So, basically, this left column, I'm just reminding you of enzyme energetics that you saw in Gen Chem and OChem. We're going to talk through it a little bit. And then we're going to talk about Well, what should be different for when we have an enzyme? And then we're going to build the enzyme version together as the final problem. So that's kind of our general state of affairs. So let's start off with energetics of a reaction. Like energetics meaning things that are related to kind of thermodynamics and delta G and energy levels and activation energy and all of that. So let's start off with uncatalyzed reactions, and let's start off with a one-step reaction. There are basically two forms that you can see of this. One is where your starting molecule is higher in energy than the other one, and one is when your starting molecule is lower in energy. So if we go from high energy into low energy, conservation of energy, that energy had to go somewhere, but we released it. And so we call this an exergonic reaction. So the features that we're supposed to be noticing here, the first one is this delta G of the reaction. That's the favorability. Here our delta G is negative since we went down in energy. And so we call it exergonic. It's a favorable spontaneous reaction. Whereas over here, we had to put in energy to get to B. We had to go to a higher energy level. Our delta G reaction here is this big positive. And so, because we had to put in energy, we say that this is an endergonic reaction. So delta G of reaction here tells us about the favorability of our reaction, the thermodynamics. One warning, closely related words are endothermic and exothermic. Thermic has to do with delta H stuff. Gonic has to do with delta G. It's easy to remember because delta G, there's a G in gonic and not in thermic. There's an H in thermic. Oh my gosh, wow. Cool. So that's our first thing that we're noticing here. Second thing that we're noticing here is delta G double dagger. So delta G double dagger, which I love this double dagger symbol. Like, it means that we are in process. It means, hold on, something's happening. It's like pausing and raising your hand to ask a question. Delta G double dagger is essentially equivalent to our activation energy. It is the energy difference between where we start and the highest point in energy here. And it's the energy that we have to invest in the reaction in order for it to do something. So our energy barrier. This energy barrier, we said it's also the like activation energy in something like the Arrhenius equation, the K equals A E to the negative RT over EA. Do y'all remember that? Is that like a weird throwback from like, I don't know, 1 to 10 years ago? Yeah, that activation energy, that's her. This is her now. Yeah, we don't need this, but like you maybe have seen this before. So the third thing is, what are these peaks? Well, that's our transition state. That is when we are in the process of making and breaking bonds. We're kind of halfway between. Classic example. For an SN2 reaction, this is the actual mechanism, right? Where nucleophiles coming in, attacking from behind, we're kicking off a bromine. The transition state looks like we are starting to make a bond to the nucleophile. We are starting to break the carbon-bromine bond. So it's like in the process of forming. This is our transition state, where we're like starting to make, starting to break. In other words, it's in transition. So those are like three basic features of a graph. And so how does this get more complicated if we have more than one step? Again, still uncatalyzed. So for multi-step reactions, we are going to have energy barriers for both steps. And so we can call those delta G double dagger 1 for the first step and delta G double dagger 2 for the second step. The other thing that we see is we have another like minimum here in the middle, and this is going to be our intermediate. So we are going to get some sort of reaction intermediate here that is this like lowered hump in between the raised humps. But back to our delta G double daggers, whichever one is our biggest, we say that step is the rate determining step. So like for this one on the right, our bigger delta G double dagger is this first one, so we would say the first step is rate determining. Whereas over here, the big one is the second step. So we would say the second step is rate determining. And you can also think about, like, again, we have delta G double dagger 1, we have it double dagger 2. We can also say, okay, going from A to the highest point, that's our delta G double dagger overall. Which, again, doesn't tell us the rate determining step. It tells us overall how much energy needs to go in. Cool. And noticeably, having multiple steps here doesn't change our delta G reaction at all. It is just from our starting material to our final product. So with this in mind, we've seen this in maybe Gen Chem and OChem 1, how should the enzyme energetics look differently when we have an enzyme involved? So one, we know enzymes speed up reactions, right? So reaction speed, that's delta G double dagger land. So our delta G double dagger for the catalyzed reaction for the enzyme should be smaller than the delta G double dagger for uncatalyzed. Otherwise, we're not speeding up the reaction, so what are we doing? We can also calculate this value that looks crazy called delta G double dagger, which is just the difference in energy between uncatalyzed and catalyzed delta G double dagger. So basically, it's like how much the enzyme lowers the activation energy. That's delta G double dagger. But it does feel ridiculous, and it does feel like closer and closer to like Wingding's font, where it's just symbols and there are no letters. This speeding up the reaction is also related to the Pauling principle, which is pretty key in biochemistry. Linus Pauling, shout out to you. Which basically just says the enzyme binds most tightly to the transition state. And so that's how it lowers the energy of the reaction, by binding to the transition state. Also, this kind of lowering energy of the transition state, that kind of lowering energy of the transition state, 1, and then 2, lowering the delta G double dagger, that is this. Making the reaction better by raising the energy of the donors, lowering the energy of acceptors, stabilizing the intermediates. All of these are the perfunctory things that lead to a smaller activation energy. So that's how our kind of mechanisms are relating to this. Cool. So now, enzymes do not affect reaction favorability. So our delta G reaction should be unchanged. We are not really changing it at all. Or it's not really, we just aren't changing it. But then the other one that's a little bit more subtle is if we want our enzyme to actually bind to the substrate, the enzyme substrate complex needs to be a little bit lower in energy than the enzyme plus substrate. So that versus this, a little bit lower in energy, because we want it to actually bind. If not, we're not going to really bind effectively. On the flip side, let's say our enzyme plus product is down here. If we want to release the enzyme plus product, we need the enzyme product complex to be a little higher in energy over here, so that it's going to want to get to that low energy state and release the product at the end. So with this in mind, let's look at the final practice here. So we need to draw a reaction coordinate diagram here for this. We have an uncatalyzed reaction that's unimolecular, 2 steps, with the first step rate determining. So what does this tell us? First step rate determining means we have a big first hump. 2 steps means we have 2 humps. Then they say it's favorable. In other words, it's exergonic. So we know that the product is lower in energy. And then they tell us to label everything. So I'm going to do that pretty quickly here. So we need to go from our starting material to our product. Our product needs to be lower in energy, so I'm going to put the product over here, lower in energy. Then we need to have a big first hump. So I'm going to make maybe big peak here, and then we get to an intermediate. So I'm going to go ahead and start labeling these. So this is our starting material. This is transition state number 1. This is our intermediate. And then transition state number 2 needs to be a smaller hump. And then we have our product. So because doing the curved things is a little bit tricky here, what I'm going to do is I'm just going to kind of connect these with big lines. So let's start off by labeling our delta G reaction. So that's the energy from our starting materials to our products. This is our delta G reaction. I'll make that a little bit smaller. And we see that we go down in energy, so it's exergonic. We're all good there. Now, let's label our delta G double daggers. So, for the first step, we have this. So that is delta G double dagger 1. And then our second one is this smaller one here. And just to make it not too cluttered, I'm going to not write it in because this one is going to be our bigger delta G double dagger. We have a bigger hump in step 1, so that means that it is a rate determining step. So I'm just going to call this delta G double dagger uncatalyzed. So we've identified our delta G double dagger. We have identified, I'll put the transition states in the color I used over there. Did I use that color? Yeah. It's a little chunky. But any questions so far on the uncatalyzed before we add in our enzyme? Or have I made any mistakes? Something that I am want to do. Okay, so for our enzyme, I'm going to do the whole thing in blue. We now want to draw the enzyme catalyzed version of this in a different color. And then we want to label all of the different states, the delta G double dagger catalyzed, and the delta G double dagger. So we're going to start at the same starting materials, but we're going to call this enzyme plus substrate. And then we said that if this is going to bind, we want it to be lower in energy. So here. But the thing that's a little bit weird is going from here to here is kind of like a whole step in and of itself. And it's going to take a little energy input. So we're going to go a little up in energy and then down in energy to get to our enzyme substrate complex. And we haven't done the first step of the reaction yet, but we went from enzyme plus substrate to our enzyme substrate complex, which is lower in energy. And we had to go over a little energy speed bump to get there. So now we're going to do step 1, but we need to lower this gap. So if that's the original height, but now we're kind of going from here, we want our intermediate like transition state here to be smaller than that. So I'm just going to put this is our transition state number 1. And then we're going to come to some intermediate over here. Boom. So with that, we can be like, now our delta G double dagger catalyzed is this. And it is smaller than our uncatalyzed delta G. So by how much is it smaller? I could be making a really like basic like geometry error here, but I think this is the difference. Am I making like a horrible geometry error here? And to be so honest, the question didn't actually ask for this. And so maybe there's a reason why they didn't ask for that, because it's hard to draw on the actual slides. So maybe let's just not do that. Okay. And then we're also going to probably lower the activation energy of the second step too. But we need to make sure it's just a smaller hump than the first one. And then finally we need to get to the enzyme product complex, which we want to be a little higher in energy than the actual products. So this is enzyme product complex, and this will be enzyme plus products. So then we make it go over one last little energy hurdle to get to our last lowest level of energy for our products. We see from the start to the finish, we wound up at the same place. We started at the same place, so our delta G reaction is going to be the same. But we lowered our delta G double dagger catalyzed. So, yay, we've done this. We've gotten through this reaction and seen how kind of the enzyme affects it. The very last thing here is just thinking through some of these things. What if the Pauling principle was violated? What if the enzyme bound the substrate tighter than it actually bound the transition state? Then, like, what would change? What would be affected? Does anyone have any ideas? If we, instead of binding the transition state tighter, we just bound this enzyme substrate complex tighter, then what do you think would be different? Anyone take a stab? After this will be done. Oh, yay, in the chat. Okay. Does it change the stability of the transition state? Uh-huh. So the whole thing was, because it binds normally so tightly to the transition state, it lowers our delta G double dagger. But if it no longer does that, then we're probably still going to have, like, still have a high delta G. And when I say delta G, I mean a high delta G double dagger cat. Not really smaller than the uncatalyzed. So that's one kind of feature that would change. And hey, why would it slow the reaction rate? Because we didn't lower the barrier. The activation energy. So that's one thing. And then the energy to separate them would be greater than the benefit of using an enzyme. Yes, that's definitely true. Larger delta G double dagger cat, great. The other thing is, like, if we have stabilized our enzyme substrate complex, if that's the most stable thing, the enzyme substrate complex will be lower in energy. So it's going to probably be like down here. And then we're still going to have a really big energy barrier. So we have this kind of well. And honestly, it's probably going to get stuck there. So instead of helping us out, if it binds the substrate tighter than the transition state, our substrate, which could just go do a reaction uncatalyzed, is going to get trapped by the enzyme in this little energy well, and it's just going to stay in the enzyme substrate complex just chilling. Like, it is just going to be unbothered and just live there. So, traps substrate in enzyme substrate complex, can't go on to reaction. Cool. So, and with that, we have enzyme energetics. So I am done for today. Went like 8 minutes over. How was the video? I think I went like 4 minutes over because we started a little bit late. So not as bad as the first one, but still working on timing because it's all new. Cool. Well, I hope it was helpful going through some of this stuff from lecture 2 today. Lecture 3 is going to really pick up on the proteases where we left off with the aspartyl protease. And it's going to go running and show you a bunch more new mechanisms. So mechanisms is really the big city that we're headed towards. But thank you for coming. Thanks for engaging. I really appreciate it. So yeah, I will stop recording.